This is my 32-bit Minecraft computer built entirely with vanilla Redstone. It's capable of executing very simple programs completely in Minecraft. In this video, I'll talk a little bit about how the computer itself works as a whole, and also about the individual Redstone pieces that make it up. The first piece of the computer I'd like to talk about is the adder. And this was the first piece I built just because it was the most technically challenging, and I figured that if I could get an adder designed to work efficiently, then I could probably get the rest of the computer to work. And so this was a failed attempt. That was my first try, and then my second try, I got something that I eventually was able to work into a component which was fast enough and also worked properly. And this is the design which I actually used in the final computer. Now, one of the reasons why this particular adding circuit was so difficult to design is because it is unique in that it does not use binary like normal computers. Now, most of the computers you'll see in Minecraft and all the computers you'll see in real life are, as of now, binary. And this makes things a lot simpler because binary logic is a lot easier to deal with. But I wanted to build a computer that was larger than most other computers that have been previously built in Minecraft were. And so to do that, I wanted to build a 32-bit computer. Now, 32-bit computers in Minecraft would require, if we were simply using whether a signal was on or off, that would require 32 different redstone lines. Instead, what I did was I used the signal strength of redstone to store essentially 4 bits of information, because 4 bits can actually store 16 different combinations, and there are 16 different possible states that a redstone line can be in. So essentially, this would divide the size of the computer by 4. So a 32-bit computer only requires 8 lines if you decide to use signal strengths. Now, the reason why this makes everything a little bit more complicated is because, one, you can no longer use repeaters to extend signals, because repeaters will amplify the signal regardless of what it is, aside from 0, up to 15 again, which completely discards all the information that was stored. And second, it's also more difficult to deal with logically. Thankfully, we have comparators, and what would have been really nice is if there was an add feature, but rather we have a subtractor feature in a comparator. And it is still possible to do addition with subtraction, as is evident from the adder design here, but it is significantly more difficult than binary systems, or if we would have had some sort of component which performs elementary addition. Now, at this point, you're probably wondering, if you're using comparators for this circuit, how on earth is it possible to add two numbers given signal strengths if all comparators do is subtract? Now, at first this seems, well, impossible. But if we take a closer look, we can see that we can actually add numbers fairly simply using this sort of circuit. So, let's say we want to add 1, and you can see the power, the signal strength, up in the upper right corner. Power is 1 plus 2. So how do we do this? Well, first, let's take a maximum signal strength, so 15, and subtract 2 from it. We're left with 13 here. Now, 13 here minus 1 is 12. And so once you do those 2 subtractions on some sort of maximum value, then you can simply subtract this new value from that maximum value, and you get 3. So 15 minus 12 is 3. And so simply from 4 different subtraction operations, we can actually do an addition operation. And this works for any signal strengths you want, as long as it doesn't overflow 16. So let's say we want to add 4 plus 9. 4 plus 9, that's 13, we know that. and now 13 right here. This works for anything under 16. This is now 6, this is 4, that's 10. You can see the power over here is 10. And so using this subtraction idea, we can actually expand this to work in the more general case. So when I refer to the general case of addition, I'm referring to the fact that inputs should not be confined to only sums under 16. For example, if we wanted to add 14 plus 14, well, this simple circuit that we have here doesn't actually work anymore. It just says the output's 15. And that's because one output can't actually represent the sum of these two, which should be 28. Now, to solve this, we need to use something called a carry bit. And what this means is that if the output of our operation can't actually hold the true value, we set it equal to 1. Otherwise, if it's a simple case like 1 plus 2 or 4 plus 6, it's 0. And this is essentially like if when you're adding two large numbers together and you need to carry a 1, that's exactly what you're doing. You're essentially adding a carry bit. Now, you'll also know that this carry bit needs to be added to the original value. And so to accommodate for a carry bit in our circuit, an input carry bit that is. So you need to have an output carry bit and an input carry bit. So to accommodate the output, that requires some different logic. But to accommodate the input carry bit, all you have to do is add an extra subtraction operation. And so this is as simple as subtracting 1 if the carry bit is true. So we can do this, add this back, put this back here, and there. So now if this block is present, the carry bit will be set to true, and an extra 1 will be added to the output. So let's demonstrate that. I'll just add, let's add 1 plus, probably 3. Yeah, 1 plus 3. So that should be 4. And if we don't set the carry bit, we get 4. Now if we set the carry bit, it should be 5 because we carried a 1 last time, and we need to add that 1. And so here, if we were to put this here, we get 5. Now in the actual case, you'd want to have some sort of movable block between these two. I didn't set that up properly, but in the actual circuit, that's what it does, is if the carry bit is set, you just subtract an extra 1. So now that we have a basic understanding of how addition can be accomplished with comparators, let's step through some of the logic in this final circuit. So this is one input and this is the other. So first we subtract from 15 our one value, and then we carry it over here and subtract from that value our other value. Then subtract from 15 that new value, and we get that intermediate sort of sum that we have over there. Now, then we need to factor in the input carry bit. And so if we follow the logic this way, we take the output, or take the value from that, bring it down here, and this gets read by this comparator, subtracted from 15 again, so that we get that sort of value before that endpoint, feed that over here, keep going, and at this point we have, I skipped this, but this is the input carry bit right here. And we can see that if this gets turned on, then this redstone line right down here will get turned off, which will turn off this piston and bring this compost bin down 1, which produces a signal strength of 1, subtracting 1 from that value. And then this, yeah, just keeps going until we reach another subtraction, which resets it back to what it should be, the final sum, and outputs it here. Now that covers most of the logic that is shown here. There is a bit more, which is if the number overflows, we need to subtract 15 from it. And this is all handled over here. That part's a little bit more complicated, and if you really want to check out how that works, I'll leave this world download available so you can check it out. So that pretty much covers all of the logic in the adder. Now, the reason I spent so much time on the add or the carry logic is because if you have an input carry and an output carry, you can actually chain these units together. So I could put another one right next to this one, and another one right next to that one. And you could have multiple digits of input. And so since I chained 8 of these together in the final computer, that allows for 8-digit hexadecimal numbers to be added. And it just so happens that the highest possible 8-digit hexadecimal number is 2 to the power of 32, which turns out to be a little bit over 4 billion. So now that we've gone through the logic for addition in the computer, I'd like to talk about how the output actually works. Now this is a lot simpler in terms of logic. However, it is fairly complicated in terms of Minecraft Redstone. So one of the biggest challenges, for me at least, was getting this design to fit within the footprint of the display itself. So this is the footprint it actually falls in, with the exception of these 2 blocks up here. And the way it works, so we can see this is the input right here. If we wanted to say input a 15, in hexadecimal that's an F, we can reset it, and click this, and we'll see an F on the output. So it goes F, E, D, C, B, A, and then 9876 all the way down to 0. And so the way it works is essentially as follows. So you have a decoder circuit here, and this is what makes up the majority of the circuit. And this is because I just couldn't think of any sort of better way to actually store this information in this footprint. I'm sure there's other ways that it could be done, but for me personally, I'm just not good enough at Redstone to be able to, I couldn't figure out a different solution. So when a certain input is selected, you can see that the Redstone block corresponding to that input is pushed forward. So if I reset, I get a pulse that makes all of these pistons retract. And then if we were to say F, E, D, C, B, A, if we wanted an A, we could click this, and we'd see that the corresponding Redstone block would get pushed forward. Now what this does is it activates this row. And this row is responsible for encoding which of the segments should light up. And so that information, each of these different lines goes to a different one of the segments. And so with the glass blocks, if it's a glass block, that means that when this is powered, it should be off. So this is a B, this row right next to the A. And since there's a glass block above it, that means that this line, which goes into the top, shouldn't be powered. And we can see that if we actually reset, select B, we can see that the top is not powered. And that's essentially all this is. There's a lot of crazy like pistons and stuff like this, and these are just purely for trying to keep it compact. So most of the difficulty with this one was compactifying it so that it's actually able to fit inside its own footprint. So the next component in the computer I spent quite a bit of time designing is the RAM. And so in a computer, the RAM is responsible for storing the programs it's executing, as well as the variables that that program is currently operating on. And so, as we've already established, it's quite easy to actually store information in signal strengths. We can just use a circuit like this, which I showed earlier. Now, the more difficult part is actually addressing that information. And this is quite similar to if you were mailing something to an address, it has to make its way through a sort of network to find that address. And the same goes for RAM. And so the way this RAM works is there's actually 16 rows. Now I only show 8 here because beyond that it gets redundant. But there's 16 different rows, and each of those rows can be addressed individually. And in each row there contain 8 memory units, and these 8 memory units correspond to each one of the 8 digits. And like I said earlier, the adder can add 8 digit numbers together, the display can display 8-digit numbers, and the RAM can store 8-digit numbers. So everything is 8 digits. And so each of these numbers can be addressed individually, but the individual digits cannot. And so this means that you can actually store 16 different numbers. Now, the way the RAM works is you have a particular address, which in this case is only one signal strength, because remember, signal strength has 16 different combinations, and so with one Redstone you can actually address an entire bank of 16 different memory units. And so if we had a signal strength of 1, it would access the first row. If we had a signal strength of 2, it would access the second row, and so on. And so this is really what I had in mind when I designed this. And this is a module of 2 rows, and these will be stacked in columns, and 8 of them would be 8 digits. In the RAM circuit, there are really 3 unique parts. So there's the input, there's the actual storage, and then there's the output. So the input, all it has to do is, if we were trying to set one of these equal to 15, all we'd have to do is set this chain to 15, and that would get passed down this line. And if we wanted to expand this downwards, we could do that indefinitely. And then if we wanted to, say, put it in this upper one, there's 2 units here, so this is 2 hex digits. If we wanted to store it in the top one, all we'd have to do is quickly fire this observer chain, so this block gets moved here and the signal can travel through. Now, if we unpower this there, you can see that it's no longer receiving that input. We can remove this, but the value is still stored. And I went for this circular pattern just because it's much easier to tile, and that's why there's not much redstone dust here. That's because it's difficult to tile when there's redstone dust, because it seems to just connect to everything. So the storage unit, we've seen something like this before. It's pretty standard. But if we wanted to reset it, all we have to do is fire this observer chain, and it removes this block and places it back. And so let me just, for the sake of demonstration, set it again. So now it's set back to 15. Now for the output, similarly, all we have to do is fire this observer. And you can see that the signal will travel as far as it can and power these observers. Now, the reason for this is simply tileability, and I could think of no other efficient way of passing signals upwards. And you know, when I sat down to think about it, I realized that there are only you could probably count the number of ways to transfer signals up in Minecraft. And this becomes even more difficult when you're trying to keep the actual value of the signal without destroying that information. So really, that was the biggest problem with this design. And but for the most part, it allowed me to tile these very efficiently. You can see that it only has a length, or a height, I should say, of 2 and a width of 3. So this allowed me to tile quite a few in a small space. Its biggest problem is its depth, though. But the nice thing is that this allows all of the data to come in from one place, and that is these bus lines right here. You can see all of it comes in from one place, and it can simply just be addressed with these buttons and other controls. And this is crucial in a computer because ultimately the RAM, the instructions in the RAM itself have to be able to address the RAM. And in a way it forms a sort of circle. And this addressing mechanism is a crucial part in gaining non-trivial behavior from computers. The last component I'll talk about in this video is the instruction decoder. Now what this does is it converts the programs, or the program in RAM, into actual instructions that the computer can execute. So in each given instruction, there's really two parts. There's the actual command to execute, and then there's some sort of parameter for that command. And so that could just provide an extra detail or something that's provided that is required to execute that command. So this instruction decoder only takes that command. So there's a set of, I believe, 9 commands that this computer can execute. Let's just take a look at out A. So all this does is it transfers whatever is in the A register into the output register. And what this means for the person using the computer is that whatever is in the A register will be displayed on those 7-segment displays that you saw at the beginning of the video. Now, this is quite easy for humans to understand, but a computer doesn't know what to do with that. So what this circuit does is it tells the computer exactly which buttons and levers to push in order to actually make that happen. And so each of those buttons and levers are actually called a micro instruction. And so each instruction is made up a set of micro instructions over a series of clock pulses. And so the out A instruction actually only needs 1 clock cycle. So this is the first one, and this is the second clock cycle, these different rows. And in the second clock cycle, what it does is it turns whichever signals that have torches on them, so in this case, the end one and this one right here, it turns them on. Now I have signs out here which represent what each of these micro instructions actually does. So this AO stands for A register outputted onto the bus. And the bus, remember, is what connects all the pieces of the computer together. Then this last one, remember there was a torch on for A out, or out A. This last one, this micro instruction, is OI. This stands for output register in. So the output register is what stores the current value that's being outputted. And when we input the value from the bus onto that output register, that's the new value that will be displayed. And so it's as simple as that. The value that's on A gets transferred over the bus into the output register and gets displayed. And every single command on the computer is just like this. There's a set of micro instructions that get used for each different command, and the set of commands which I have created are capable of every single possible computation. And so there you have it. That's a run-through of all the major components of this computer and how they work. If you want a more detailed walkthrough of any particular component that I didn't go through today, let me know. I'll also have a world download that you can check out if you want to experiment for yourselves. I will warn you that actually executing anything on this computer takes an extraordinary amount of time. Unfortunately, just due to the constraints of Minecraft and the very slow method of moving information around, this computer is not very fast. And it is quite difficult to create quick computers in Minecraft. Not so difficult to create just computers. So that's all for this video. Thank you so much for checking out my computer. I hope you found it interesting or cool. And yeah, I'll see you in the next video.